Now, in these materials, which are formed from these ultra-thin layer of cobalt and nickel on this black layer, not shown, this is the layer of platinum, then the platinum itself becomes significantly magnetized. And in fact, the anomalous Hall signal we derive is mostly from the proximity-induced moment in platinum, which is a very interesting material I will come back to later. And now we can reduce further the width of the racetracks from 200 nanometers to below 50 nanometers, and we can follow the evolution of a single domain wall along a racetrack. This is the optical image of a wider racetrack. As we introduce current pulses, the wall will systematically move along the racetrack, and we can determine that motion from this. And the individual domain wall, single domain wall, we can follow as it moves along the racetrack in one direction or in the opposite direction when we reverse the sign of the current pulses. And it turns out then we can manipulate these domain walls so they will sit at individual positions along the racetrack to an accuracy of about 30 nanometers, and separating one domain wall position from another by 100 nanometers. These are locally pinned by the reduced current density in the vicinity of these local Hall bars we're using to detect this motion. So this we've been able to show we can move domain walls with a precision of a few tens of nanometers by current pulses along these racetracks as narrow as 50 nanometers. This in fact is relevant. The length scales are suitable for many applications. And I also wanted to mention this is work by Jay Chun in my group, Jay Chun Jun, where we've been able to demonstrate the motion of individual domain walls backwards and forwards under a tunneling junction device that enables us to detect the position, whether the magnetization is in one direction or the opposite. Beneath the tunnel junction device, we can detect with high accuracy the domain wall, and we can demonstrate we can move the domain wall backwards and forwards at speeds of sub 500 picoseconds, which means this kind of racetrack, a single domain wall racetrack, is very interesting for applications to replace the fastest memory today. So we can replace the slowest memory, VNAND, to the fastest memory, static random access memory, using this racetrack memory technology. The goal is to have many, many domain walls in a single racetrack, in a vertical three-dimensional racetrack. And I'm not going to discuss our work on three-dimensional racetrack, but we have several projects in which we've been able to demonstrate that possibility. I want to switch instead to the main focus of my talk, which is on the Josephson Diode effect. And I wanted to remind you briefly about this material, manganese-3 tin. It's actually a very interesting material which has several structures, and one of which is hexagonal. And this hexagonal crystal structure has a Kagome plane shown in this cartoon. This is one layer. And the black atoms correspond to manganese atoms, which are magnetized. And in between these triangles of manganese atoms, there are tin atoms shown as these purple atoms. And the triangular structure means that the manganese atoms, which want to be coupled antiferromagnetically with respect to one another, form rather this triangular lattice in which the moments are oriented at 120 degrees to each other. And it turns out this system has a vector chiral structure because of the tin atoms through a Dzyaloshinskii-Meria effect. I'm not going to talk about this, but this term, this vector exchange term, is very important in causing the structure to have this chiral Kagome triangular lattice. And why is it interesting? Because on the one hand, this structure has no net magnetization. However, it turns out that because of the slight anisotropy, where the magnetic moment pointing towards the tin has a slightly lower energy, this means that in the plane of this structure, there's a small remnant magnetic moment, but it's very, very tiny. But we could use that remnant moment to orient the system into a single antiferromagnetic domain structure, which is important. And the reason for studying this originally was because of the theoretical prediction by Kubler and Claudia Felser, who visited you early this year, where they predicted that this manganese-3 tin system should display a non-zero anomalous Hall effect, even though the magnetization is essentially zero. And at about the same time, Alan MacDonald at UT Austin and his group predicted that a related system, manganese-3 iridium, which is a cubic system, not hexagonal, but it also has this Kagome lattice on the 111 plane, no net moment, so it's impossible to set it into a single domain, very difficult. They also predicted that these types of systems should display an anomalous Hall effect that is non-zero. Normally, the anomalous Hall signal is proportional to the magnetization. When you have no net magnetization, it should lead to zero anomalous Hall signal. These two groups predicted rather large anomalous Hall conductivities. And so we were one of the very first to detect this using some single crystals made by Claudia Felser in her group in Dresden. Then Ajay Nayak, who was a postdoc in my group at the time, showed that these single crystals displayed a very large anomalous Hall signal. This is shown here, the anomalous Hall conductivity, as a function of angle of an applied field. When we apply a field in the Kagome plane, we can rotate the lattice around that plane from one easy direction to the opposite direction, and you see that the anomalous Hall conductivity changes from one value to another large value. These are very large values. And so we indeed confirm these predictions that this system shows a very large anomalous Hall conductivity, but only when the current is flowing perpendicular to the Kagome plane. And at the same time, Satoru Nakatsuji published a related paper that we actually worked on manganese-3 germanium. They worked on manganese-3 tin, and they also observed a large anomalous Hall signal. Now, why is this interesting? So first of all, let me just remind you that this is an hexagonal system. So that means there are 6 equally favored directions or orientations for the Kagome triangular lattice. There are 6 equal directions rotated by 60 degrees, and in between you have a high energy configuration. And this is some work we did with Björg Berger and Ingrid Matic at the Martin Luther University. They calculated the energy of the system as the Kagome triangular lattice is rotated in the plane, the hexagonal plane, and as a magnetic field is applied perpendicular to that plane to bring the moments out of the plane. And as you bring the moments out of the plane, then the energy barrier will decrease eventually when they're aligned with respect to one another. It's a high energy state, but there's no preferential orientation. So why am I telling you all that? Because what's of interest is to see whether we could use spin-orbit torques to rotate this Kagome lattice. And so I'm not going to discuss this in detail, but what we have shown is that indeed you can grow this manganese-3 tin anti-ferromagnetic layer on top of a heavy spin-orbit coupling layer like platinum or tungsten, and a current through that platinum layer will generate a spin current. The spin current transverse to the charge current through the spin Hall effect. It passes into this layer, but it only affects a very thin interface layer. Yet you can switch the orientation of the domain even when this layer is very thick, up to 100 nanometers thick, well beyond any spin diffusion length. And the reason for this is, we believe, is that the current, as well as providing a spin orbit torque from the spin current, it also, of course, provides heat. And what happens is, heating is very important. So the system originally in one state is heated by the current passing through it, and the current passing through the neighboring platinum, could be tungsten layer, provides torques that sets the state of the interface layer. And when you turn off the current, the system will cool down, and if it cools down in the presence of this spin orbit torque, then essentially the interface cedes the state of the complete layer. So this is a very interesting notion for setting actually whether it's and what we showed here was that if the current pulse we use, which is of the order of a few hundred nanoseconds or a few hundred milliseconds, if the current pulse is turned off too quickly, very abruptly, on the scale of sub-nanoseconds, then the setting of the magnetic wave is suppressed because the system will cool down in the absence of any spin for the source, if the current of 250. In this way, we could prove, indeed, that the system is rotated by previous mechanism due to the spin for the source. Anyway, cut a long story short, the program wrote the structure into a single state in this way, irrespective of the useful interesting previous mechanism. And I'm not going to say much more about this, except to say now, I want to switch to the topic, my main topic in the course, is the Josephson Diode effect, so it's a long introduction. And this is some very nice work by Stuart S.P Parkin. What he did, he took this layer of manganese to uranium, and this is in turning this stuff in this green layer. And on top of this blue layer, a simple electrode wire formed from iodine superconducting. And what we wanted to see was whether the superconducting current could flow from one iodine electrode through this green manganese into second electrode. In other words, by proximity, could we induce superconductivity into this spiral negative magnet? The reason for this is that, as shown on the left hand, the iodine is a conventional X-ray superconductor, and it's the condensate formed from superpairs, in which the spins in the pair are antipairs, and the momentum are antipairs, with no net spin on the superpair. However, it was proposed 20 years ago, that's the pleasure, and it proves that better, that if you introduce superpair from conventional superconductor into a system in which the magnetization is non-linear, so it's a magnetic system will usually suppress superconductivity because it favors electrons one spin, whereas in the superpair, the electrons opposite spin. The idea was that in a non-collinear spin texture, nevertheless, the triplet, the singlet pairs are converted to triplet pairs, and these triplet pairs can exist over long distances. And what Kunrock could observe was he observed a long-range supercurrent flowing from one electrode, niobium, to the other, which the mechanism is due to the formation of spin triplet pairs, we suppose. So this is the argument, and we published this in Nature Materials 2 years ago. So what you see, you basically see that if you measure the current between these two niobium electrodes, and D is the spacing between them, you see that the voltage is 0 for small currents until you exceed some critical current, and then you start to observe a voltage. Becomes basically the IV relationship becomes linear, just like a normal resistor, once you exceed this critical supercurrent. But below this critical supercurrent, then there's no voltage drop between the niobium electrodes, but we can flow current dissipationless through this manganese-3 germanium chiral antiferromagnet. And of course, what you see is if you increase the separation between these niobium contacts, then the critical current or the critical voltage below which the supercurrent will flow will decrease. So the wider the spacing, the smaller is the maximum supercurrent that can flow. So this was the first time that these long-range supercurrents had been observed through such a non-collinear antiferromagnet. And this is at relatively high temperatures, as you can see here, up to the ordering temperature of the niobium, which is about 5 degrees Kelvin in these thin films. So why is this interesting? And the interest is this. There's a paper by Bustin many years ago, 40 years ago, where he, of course, showed that if you have a superconductor in proximity to a ferromagnet, then again, because the Cooper pairs, as you can see, are formed from electrons with opposite momenta and opposite spin, in a ferromagnetic system where the conduction bands will be spin polarized, so that there will be different numbers of spin up and spin down electrons at the Fermi energy, and they may have different Fermi wave vectors, then it's not possible to combine electrons with opposite spin unless they have a finite net momentum, finite momentum. This is possible to form a finite momentum spin triplet state. But the order parameter for this state in the ferromagnet will decay with an oscillatory component. This is the work by Ustin. What Bergeret showed was that, so the idea is you take a conventional S-wave superconductor and proximatize a neighboring ferromagnet, and then you will have the superconducting order parameter will have both a singlet and a spin triplet component. Spin triplet, the spins are parallel, could have net zero, could have a net angular momentum, but since it's a S equals 1 state, it could also be S equals 0. So what Bustin showed was you get an S equals 0 spin triplets are generated with an order parameter that oscillates in space away from the interface between the superconductor and the ferromagnet. Now what Sebastian Bergeret showed was something more interesting, that you could sustain S equals 1 spin triplet superconductivity by combining a first ferromagnetic layer. If you look on the right-hand side, this is just some recent experiments. This is by Ivan Kindiak, a PhD student in my group, and Swapna Mishra, who's a postdoc in my group. And what they're doing is looking at vertical Josephson junctions, niobium on the top, niobium on the bottom. These are made by sputtering. And you see there's an initial nickel layer whose magnetization is in plane. That would cause the formation of these S equals 1 triplet states. But there's a second magnetic layer, which is formed from atomically thin nickel and cobalt layers, just like our racetrack, which is perpendicularly magnetized. And according to Bergeret's calculations, this will generate S equals 1 spin triplet states that will decay very slowly over distance. And this essentially is what Ivan and Swapna are seeing. They look at this critical current density, and on the right-hand side, as they increase the thickness of this middle perpendicularly magnetized layer, they see a very small decay in the critical current. However, on the left-hand side, it's the same structure as this right-hand structure, but no, this first in-plane nickel layer is missing. And in this case, you can see that the critical current rather decreases rapidly as a function of increasing thickness. This would be because it would be similar to what Bustin was proposing, and this structure is similar to what Sebastian Bergeret was proposing. So the concept is non-collinear structures can sustain triplet superconducting pairs over relatively long distances. And triplet pairs in the S equals 1 or S equals minus 1 state are super interesting because they carry angular momentum. And I want to come back to that later. We want to use that angular momentum to manipulate magnetization. This is our goal. So let me now turn to briefly the diode effect. So I've shown you a structure in which I showed you that the critical current in manganese-free germanium in a lateral Josephson junction, I didn't mention it, but the critical current, if we go back briefly, wanted to mention this. The critical current flowing in the positive direction is the same as the critical current flowing in the negative direction. They are identical. This is what people have believed for many, many, many years, although our host predicted, he reminded me, in 2007, predicted that the critical currents could be distinct. Okay, I want to come back to that. So now we believe, so now switching the same topic, switching materials. We're now going to use a material, nickel ditelluride, for a very special reason. This is work by Anibir Powell, postdoc in my group, and others. And this material is a van der Waals two-dimensional metal. I think you're all very familiar with the van der Waals systems. They're super interesting because they form layers in which in this case, you have a nickel layer and a tellurium layer on top, a tellurium layer underneath. And these nickel-tellurium layers are strongly bonded, but they're very, very weakly bonded, this tellurium layer with the next tellurium layer. And in between, you have a gap, the so-called van der Waals gap, which is weak. It means you can therefore mechanically exfoliate thin layers from a single crystal using simple mechanical exfoliation means, the same technique that Andre Geim first used to demonstrate a single layer of graphene. So here we are, we take this material, we're not going to make single layers, but nevertheless we make thin layers. And the reason why we chose this system is it's non-magnetic, And it turns out it has a centrosymmetric crystal structure. So it breaks neither time reversal symmetry, it's not magnetic, and doesn't have any hidden time reversal symmetry breaking phenomena, which is a very interesting topic today, nor does it have any crystal symmetry breaking. Therefore, we should not see any diode effect. However, it has so-called topological surface states. It's a topological metal. It's a Dirac semi-metal with a topological surface state, which people knew was spin polarized from photoemission experiments. So what do we do? Here's one of our samples. You see here, can you see this layer? Yeah, you can see my arrow. This is the nickel ditelluride flake. And then we simply use electron beam lithography to make niobium wire. So these are niobium contacts, all to the same wafer. And they're separated by these three separations, 120, 350, and 580 nanometers, you can see here. Now, what do? We measure the voltage between two neighboring, or two of the niobium electrodes. And as we reduce the temperature, at some temperature, we see a drop in the voltage. This corresponds to the superconductivity appearing in the niobium electrodes. And at a lower temperature, we see proximatized by the niobium. So this is very interesting. We've made a non-superconducting material superconducting. And what is really amazing is that this superconductivity persists here over 580 nanometers. This is a very long length scale compared to any characteristic length of the superconducting state, let's say in niobium or in the proximity induced state. So it proceeds over very long distances. And in other subsequent measurements, we've shown that this superconducting state can persist even up to a micron spacing between these niobium electrodes. This is very remarkable. So again, you can see here that the transition temperature of these niobium electrodes remains the same, but the transition temperature of the nickel ditelluride, the junction, drops as we increase the spacing, which is not so surprising. Now again, we can measure then the voltage. So I've changed the axes. This is the voltage on the vertical axis. This is the current on the horizontal axis. These are for these three different spacings of the niobium electrodes. And you can see if you take the blue, you can see at low currents, the voltage is 0 between the niobium electrodes, lateral Josephson junction, and above some critical current, a voltage starts to appear. Actually, it's this voltage starts to appear. And when you reverse the current, then the system will become superconducting here. But we're going to concentrate on this critical current density, the critical current which you go from the superconducting into the normal state. You can see this hysteresis. This is very typical for Josephson junctions of this type. However, you can see again that the critical current in the positive direction for superconducting to non-superconducting state is the same whether the current flows left to right or right to left. Okay, just as we showed for manganese 3 germanium. However, if you now apply a small in-plane magnetic field to break time reversal symmetry, when the in-plane magnetic field is perpendicular to the supercurrent, in other words, it's parallel to the electrodes here, then you see very clearly that the critical current flowing to the right is much smaller than the critical current flowing to the left. You can see very clearly, right? Giant effect, actually. Supergiant effect. The magnetic field we need is about 20 millitesla in the plane perpendicular to the supercurrent flow. So this was one of the first demonstrations, we think is the first demonstration of this Josephson diode effect. Prior to this work, there was some very nice work from Ono's group Teruo Ono's group in the University of Kyoto, where he showed in a tricolor superlattice, niobium, vanadium, tantalum, he could see a superconducting diode effect. Not clear what entirely breaks the symmetry in that system. Nevertheless, here it's clear what breaks the symmetry, time reversal symmetry, is broken by this magnetic field. I'm going to come back to that in a moment. So what do you see? We simply take the difference in the critical current flowing to the positive and the negative directions divided by the average. We're going to use that as a criterion. So this delta IC, we plot the difference in the critical currents, positive and negative, as a function of the magnetic field when it's applied perpendicular to the direction of the supercurrent. So no field, no diode effect. As you increase the field, the diode effect increases to a maximum value. And then as you further increase the strength of the magnetic field, it decreases, crosses zero, changes sign, and in fact will oscillate as a function of increasing magnetic field. And if we look close to the ordering temperature, we can also see that the magnitude of the asymmetry scales with temperature towards the ordering temperature of the junction with a particular characteristic temperature dependence. In fact, it goes like temperature minus the temperature of the superconducting ordering temperature of the junction to the power 2. So in collaboration then with Liang Fu, Margarita Davidova, and Yang Zhang actually was a former postdoc with Claudia, then they developed this theory in which they introduce into the free energy of the system. The free energy of the system is related to the superconducting order parameters in the two electrodes, and they introduce a second order contribution which is related to tunneling of not single Cooper pairs but two Cooper pairs. And as soon as you introduce this and you calculate the so-called current phase relationship, how the current varies with the phase of the superconducting order parameter, then you can account for this non-sinusoidal relationship. You have this additional term that goes as the superconducting order parameter to the power to the 4 in this way. And this is the difference in phase of the individual Cooper pairs and the double Cooper pair tunneling. And in fact, they calculated that this is the behavior we should expect to see, how the critical current asymmetry would vary as a function of this phase angle. And they also calculated, based on this, that indeed, as we see, the variation of this asymmetry should vary like t to the minus the junction temperature to the power 2, which is what essentially we see. That's that red line. This dependence here from their calculation can be shown as this. This is what they calculate for the asymmetry in critical current as a function of the direction of the field we're applying with respect to the direction perpendicular to the supercurrent. Let me say that again. So if you go back here, we're applying a field in the y direction, which is along these wires. It's perpendicular. The supercurrent is flowing here between the niobium electrodes in the nickel ditelluride, and we apply a field in this y direction. Now we change the direction of that field by rotating that field in plane. And only when the field is perpendicular do we see this effect. When the field is along the supercurrent direction, the effect goes to zero. That's what we find experimentally as shown. This is our experimental data. This is the angle by which we've rotated the field away from this direction of maximal effect. And you see it has this relationship, which seems to be sinusoidal relationship, well predicted by this theory. And as you increase the magnitude of this magnetic field, then you see that the system, first you see the system changes. This is the smallest field, 2 millitesla, 10 millitesla, the effect gets bigger. But as I already showed you here, if the field is too big, it will actually get smaller again and change sign. And this region, you see a more complex pattern in our experiment, which appears to be well described by theory within all the errors of the theory. So this is our experimental curves. This is the in-plane magnetic field. This is the angle of that field. And this is the asymmetry in the critical current. So red and blue are opposite directions, white is zero. And it seems to be well described by this theoretical model. Don't you agree? Anybody agree? What's the yeah, the Van der Waals system itself. Can I come back to that later? It's a very interesting question. We haven't addressed it, quite frankly, in this nickel ditelluride system. We've addressed it in tungsten ditelluride. So it's a very interesting question. Let me come back to that in 1 second. Okay, so the basic idea is we've seen this effect is giant, up to 80%. And it can be accounted for theoretically if you phenomenologically introduce a new term in the current phase relationship. It's a phenomenological model, and we actually have we've compared the experimental parameters with theory, and there's some kind of fudge factor, I must admit a G factor, which is very large, but nevertheless seems to account for the basic angular dependence and temperature dependence very well. To do this, we need to break time reversal symmetry. And as I mentioned earlier, this system, these are actually some very nice work by Niels Schroeter, who's an independent group leader in my institute. He's carried out some photoemission experiments. And in this system, nickel ditelluride, it was known, though, I'm not going to go into detail, there's some surface electronic states which are spin polarized. And this is shown in this calculation. And so what happens is at the Fermi energy, you have states which are spin momentum locked in this system in the surface. And so as soon as you apply a magnetic field, you split these states. So it's a little bit complicated. This is momentum. They're polarized out of the plane of this diagram. So when you apply a field in that direction, you get an exchange splitting that will then break time reversal symmetry and allow for this non-reciprocal diode effect. So we have evidence in this system that the system displays time reversal symmetry breaking through these topological surface states, which is why we chose the system to explore. So why are we interested? And I'm going to come back to your question in one moment. We're interested because I'm super interested, as I mentioned at the beginning, in this concept of building a racetrack memory where we would have a magnetic wire with many magnetic domain walls, which at room temperature, we pass a current through, we create spin currents through a variety of effects, but in particular through the spin Hall effect. Those spin currents carry angular momentum. They diffuse into the magnetic layer, cause torques, and cause the domain walls to move very efficiently. We've demonstrated at speeds exceeding 1 kilometer per second. Well, the idea here is if we can create triplet supercurrents, through the mechanism I described earlier, through manganese-3 germanium, these triplet supercurrents carry angular momentum. And can we introduce them into our magnetic racetrack and therefore move the domain walls? And I tell you today, the critical currents that are available are too small, we believe, to manipulate the magnetization. However, we can reduce the magnetization at the temperatures at which we want to do this, which is basically 10 millikelvin. We can reduce the magnetization 100 times, maybe 1,000 times, and then the moments will be sufficiently small that these critical supercurrents should be able to manipulate them. So that's currently what we're doing. We haven't done it yet, but we're attempting to make very low moment magnetic compounds. It's not easy, which can have very low Curie temperatures, we don't care, but would have sufficiently low moments that we could manipulate them with these critical currents, which we have. We're close to doing it, I think. At the same time, this diode effect is a very interesting sensing device, we believe. So the idea is that, if the magnetization in this racetrack points in one direction or the other, we'll see we'll see a zero voltage, or we'll see a finite voltage. So we can detect magnetization simply from the presence of a voltage across this Josephson diode. Could be. And so basically it's a pretty low energy reading, very sensitive device, and this would be a low energy means of manipulating these domain walls. So why are we interested? I have to say we're interested here because I believe for quantum computing systems, you need conventional quantum computing systems are basically an analog technology, but you need digital memory to set the states of the quantum memory and to store the reading out of the quantum memory. You could do this using non-quantum memory. You could use it using conventional memory. If you could build a conventional memory that operates at ultra-low temperatures, which is what you need, the same temperature as the qubits. No such memory exists today. I think this is a fantastic way of doing that, and that's what we're working on. So let me tell you, since we're running out of time, I want to tell you two other Josephson diode stories just very briefly. And this is one really interesting one where we've shown that we could create a Josephson diode using not nickel ditelluride, but using platinum. So platinum is really very simple. And we grow this platinum on YIG. So YIG is a garnet. It's an insulating oxide. It's a ferromagnetic system, but it can be magnetized, and it has a remnant magnetization. So we magnetize it in a direction perpendicular to the flow of the supercurrent. So the platinum on the bottom surface becomes magnetic. And it turns out platinum is readily magnetized. So as I mentioned, in our conventional racetrack, the platinum layer in which we're creating spin currents carries 30% of the magnetization of our racetrack. So this becomes magnetic in the bottom layer. This platinum is 10 nanometers thick. The magnetic region is about 1 to 2 nanometers in extent. So on the top surface, we introduce conventional S-wave Cooper pairs from niobium. And well, what we find indeed the distance between the niobium electrodes has to be relatively small. Here it's 100 nanometers. Nevertheless, we can make this magnetic platinum superconducting. So that's pretty amazing. It's both proximatized into a magnetic state and it's proximatized into a superconducting state. And so now switching the axes again, here is the current, again, flowing from one niobium to the other through platinum, which is magnetized on the bottom surface. And what you see is, you can see the orange curve, the critical current in one direction is different from the critical supercurrent flowing in the opposite direction. And if we change the magnetization in that magnetic layer, this YIG, we switch it from this direction to the opposite direction by applying a big magnetic field. But then in zero magnetic field, we carry out the experiment. You see the green curve, we've exactly changed the asymmetry. So the asymmetry in the critical currents depends on the direction of the proximity-induced moment in the platinum, and we can revert it by simply changing its direction. And of course, we can make it go to zero if we proximity magnetize it along the supercurrent direction. And so what do we find then? Again, we see very large zero bias, zero field now, zero field. No, we don't need any external field. We only have the remnant induced magnetization in platinum. And we see this diode efficiency then drops as a function of increasing temperature till we reach the transition temperature of the platinum here. So we, in this case, and this actually is at 2 degrees Kelvin. The previous experiments I showed you were at 10 millikelvin. So it's a much higher temperature. Nevertheless, we see a zero field diode efficiency of about 35%. In the previous case I showed you, it was up to 80%. So I think this is really interesting. We use two proximity effects, magnetism and superconductivity. Amazing. And of course, platinum is a key material in our racetrack. So now we could use our magnetic racetrack, proximatize the platinum into a superconducting state, and we believe create triplet pairs to propagate into our racetrack. So let me go back to your question, which is a very interesting one. And to answer your question, we've done a different experiment. So here we've taken tungsten ditelluride and we formed a vertical junction. So we've exfoliated layers of niobium diselenide, which is another van der Waals layered material. A layer of niobium diselenide on the top and one on the bottom. And in between, we've exfoliated a layer of tungsten ditelluride. This actually has a non-centrosymmetric crystal structure. It's orthorhombic due to distortions in the lattice. And what we do now is, because the supercurrent is flowing vertically, we can then rotate this magnetic field in the plane of the tungsten ditelluride and see when the effect is largest or smallest. So first of all, we do see a Josephson Diode effect. You can see here. Can you see in the presence of a field, a small in-plane field. So now applying an in-plane field, which is perpendicular to the supercurrent, but we can apply it in any direction in the plane of the tungsten ditelluride crystal. And what we find, of course, is that we only see the diode effect when the field we apply is both perpendicular to the supercurrent, but is along a single direction in the tungsten ditelluride plane. So this is really interesting. Okay, I just show this is what we see. First of all, we also see that, okay, going back to this one, can you see this thickness of the tungsten ditelluride? Now we can make it very, very thin, easier than by the lateral junction. We need to use electron beam lithography. Here we just rely on the thickness of this layer to separate the two superconducting electrodes. We can go down to 2 nanometers, and we see a diode effect, and 7 and 60. And what we find is that the magnitude of this diode effect increases the thicker is the tungsten ditelluride. So it's related to some critical thickness of the tungsten ditelluride, which we think is very important. More importantly, as I mentioned, these are 3 different flakes of tungsten ditelluride. This is work by Jaekun John in my group. And what he's done is he's made flakes, 2 nanometers of tungsten ditelluride, 7 and 60. And he's now looked at the diode efficiency as a function of direction, fixed field. This is 200 millitesla, this is 20 millitesla, this is 3 millitesla. It's really complicated. And we rotate the field in the plane, and we can determine by polarized Raman the orientation of the tungsten ditelluride lattice. And then we see this is the magnitude of the diode effect. And you see it's largest along a given direction. And it turns out it's always largest when the field is applied upon the A-axis, one plane in this tungsten ditelluride, which I told you is orthorhombic. So we have a clear connection between this diode efficiency and the direction in the crystal plane in which the field is applied. So that answers your question, and this is very interesting. We didn't explore it in the nickel ditelluride. It's difficult to explore because you have to lithographically pattern too many devices. Here we can, in one device, we can show how the effect is determined by the orientation of the magnetic field relative to the crystal lattice. And therefore, it's important for 2 reasons. One is it tells us something about the origin. More importantly, it says it's truly an intrinsic effect. So it turns out that if you have large devices, you can either have asymmetries in the distribution of current flowing through the device that can lead to asymmetries and diode effects, or you can have trapped magnetic flux that will disturb the distribution of current and similarly give rise to an asymmetric diode effect because you have a supercurrent flowing due to the trapped flux, which will add or subtract from the current flowing in one direction or the other. And so a big controversy has been in this field, is the effect truly intrinsic? So we believe these experiments prove that it's intrinsic. And I must admit, we've had this paper under review for a year now, and we're still arguing with the referees. I don't understand. It's a fantastic paper. Why they don't accept it? Anyway, eventually we hope they will. And so this is very interesting. We prove it's an intrinsic effect, clearly related to the crystal lattice as your question. And we can also show that if we use a centrosymmetric barrier from a similar material, moly ditelluride, these data are not so good. We've got much better data now in response to these referees, and then we see no effect. So you need to have both broken crystal symmetry and this broken time reversal theory to see the effect. This just shows you how the asymmetry is a little bit technical. It's divided by low field. Anyway, the magnitude of the diode effect increases with thickness up to some critical thickness of the order of 30 nanometers. It'd be difficult to see this in lateral junctions, and we see again the dependence on temperature following the same temperature dependence that I discussed earlier. So I'm going to come to my conclusion. So first of all, chiral antiferromagnets are not only very interesting because they can, in many respects, look like a ferromagnet, even though they have no net magnetization. And in particular, they display large anomalous for conductivities. Sartoro has also shown large other properties I'm not going to discuss. And this led us to show long-range flow of supercurrents through magnesium-3 germanium. But we also see now diode effects. I discussed nickel ditelluride in lateral devices, tungsten ditelluride in vertical devices using niobium diselenide as the electrodes. We have also had some very nice work on lateral junctions using platinum ditelluride. And I think this is fantastically interesting, this proximity-induced magnetization and superconductivity in the simple material platinum. where we can see very large non-reciprocal behaviors. And we have a model which for finite momentum Cooper pairing, that's actually a very old model, which does account for our angular and temperature dependence. And our main goal is eventually to demonstrate the possibility of manipulating chiral domain walls or magnetization by triplet supercurrents, which would be dissipationless at ultra low temperatures, and to detect domain walls using this Josephson Diode effect. So I want to thank you very much for your attention.
Because Professor Hu is attending another conference, so they asked me to chair the questioning session. So is there any question?
Thank you for a very nice talk. I have two questions.
Okay.
First of all, it's for this case of this platinum, for this proximity effect, both sides. You have the bottom this magnetic proximity effect, and the other side is superconductor. But you said that the thickness of this platinum is around 10 nanometers.
10 nanometers, right?
And this penetration taps for this proximity effect is about 1 nanometer.
Yeah. Okay, yeah, very good.
And then how this can couple for both sides?
Because the superconducting condensate, of course, extends over the whole 10 nanometers. So, of course, you can see the bottom interface. And so that's how it works. The whole of the platinum doesn't need to be magnetized, only a portion of it, within the superconducting order parameter, some kind of coherence length. So if we make the platinum too thick,
so this,
it will go away.
This superconducting coherence is much longer than 10 nanometers.
Yeah. Oh, 10 nanometers, let's say. If we make it much thicker, then the effect we find is diminished.
The second is about this nickel telluride. Nickel silicide or telluride.
This what?
Nickel telluride. NISE.
Oh, yeah. Sorry. This one. Go back. This one. Yeah. Nickel telluride.
Yeah. This one, you have external magnetic field, which is perpendicular to the current.
Perpendicular to the current. Yeah.
But the density of the internal magnetic field is the size of millitesla.
Yeah,
so
millitesla.
Something around.
Yeah. Good question.
But this is too small.
No. Yeah, it seems very tiny.
How we expect such a strong effect?
This is why we need your help. So this is why I said that the theory appears, it does account for angular dependence and the temperature dependence and the field dependence, this angular, you see this complex field dependence that we observe. However, this complex angular dependence, however, you're totally correct. As I mentioned, we need a very large G factor because the field is so tiny. Yeah. So
but
this is the only
G factor is, I don't think it would be so large. So this
it's because it's probably, we think it's these topological surface states, so it's not so straightforward. In other words, this at least explains why you need the field perpendicular to the current, right? Because of the spin momentum lock-in. Yeah. So it has to be, this works. However, I agree with you, this is something that we have to think about how to explore. But you're totally right. This is the G factor, it has to be like 300, which is probably too big. Yeah. But since it's associated with this topological surface state, maybe it has some interesting value because of that. We don't know the answer.
Okay.
But that's a very, very good question. Thank you.
Thank you.
Are there more questions? Yes, Zhe.
Thank you for such nice data and presentation. And actually, I have two small questions. One is about this 5-0 phase. And because it's quite interesting, apparently the silicon diode definitely results in 5-0 phase. And do you have any data about this 5-0 phase?
Oh, I'm not sure I could.
The 5-0, the anomalous phase.
Yeah, the normal state. Yeah.
Yeah. The 5-0 anomalous phase.
Oh, I'm not sure I understand the question. Maybe you could explain.
Yeah. Okay. So
sorry.
because it shows some result about the anomalous phase, right?
The normal phase. Oh yeah.
Yeah, anomalous phase, the 5-0 phase,
Mhm.
the phase shifting. So I'm wondering whether you have some experimental data to prove this.
I mean, you're talking about this theoretical,
Yeah,
theory from Liang Fu. Yeah, this
no,
is
the
no?
previous one.
This one.
No, the previous one. Maybe
Oh.
two slides before.
Oh, this one back here. This one.
Anyway, that's fine.
Well, we could talk later.
Yeah. Doesn't matter.
Yeah.
Another question about this application. So I think one important parameter for the application is the switch power, right? How is the switch power in this system actually? So it's your magnetic system.
Oh.
Switching power.
How much current do we need?
The current, all the switching power.
Switching power.
Yeah.
Okay, this is a super interesting question. We don't know the answer. So basically, if you take a super current, you've got to propagate it across an interface. And at an interface, all sorts of interesting things can happen, because to get a Cooper pair from one side into the other, on the one hand, you can proximatize the neighboring layer into a superconducting state. On the other hand, the supercurrent can be repelled, and you can get, for example, Andreev reflection and other effects. So this is an unanswered question, I would say. So what we have to demonstrate is, can we find a magnetic material which will allow the supercurrent basically to propagate into that magnetic material over a long enough distance to transfer angular momentum into the magnetic state? This is the key question.
Okay.
It's a very good question. We haven't demonstrated it. Nobody has. So it turns out, let's say, you could say what we're working on here is a field of what we call superconducting spintronics, which essentially started 20 years ago with the work of Sebastian Bergeron. And over the last 20 years, there have been 3 or 4 demonstrations of this concept of triplet supercurrents, mostly completely, it's the observation of long-range supercurrents flowing through distinct materials. For example, holmium. There's a science paper by the group from Cambridge, maybe 10 years ago, and that paper it's a very, I would say one has to be a little bit skeptical, because it was on some amorphous polycrystalline holmium, where you're relying on the beautiful helical state that holmium is known to form in bulk at low temperatures, and they claim this helical state would allow the propagation of supercurrents. However, it could just be you have a non-collinear random spin polarized state. So anyway, the point is that there have only been a very few experiments, and there have been no experiments yet to demonstrate the possibility of either switching or, for example, exciting. You don't necessarily need to switch. You could RF excite a magnetic moment under resonance conditions, which might be easier, and detect that resonance. That's something we're working on as well. So I think this is a very, very interesting question, which has yet to be resolved, and is the key question. So all I'm saying is that in 20 years of superconducting spintronics, nobody has yet demonstrated a supercurrent that can manipulate a magnetization. There has been a lot of work on Andreev reflection from ferromagnets, and using Andreev reflection to determine the spin polarization of the ferromagnet. These are in strong ferromagnets. So our goal, we believe, is to make weak magnetic systems, and under those circumstances, at least I expect we will be able to manipulate magnetization through the passage of these supercurrent, the critical pairs.
Okay, thank you very much.
Thank you very much.
Oh, I think, okay, yeah. So you may check online if there are any questions.
Okay, thank you for this nice talk. I agree with you. Your result, the functionality, and your future plan integrate this functionality into like your proposed restrict memory. But my issue is how to understand this result in physics. Is there's really spin triplet superconductivity and the because and the finite moment pairing, because like your evidence is not enough strong to claim such a result. How about your other evidence like the apocryphal field?
Yeah. So the question was, I think, the question was the question, to date, there are no known triplet bulk superconductors on the one hand, except for most recently uranium ditelluride. And as you know, before that, strontium ruthenate for 20 years was believed to be a triplet superconductor, but now those same authors have decided it is not. So there's only one example, uranium ditelluride, some very beautiful recent work. I mean, I think this is it's a very interesting question, and I think, to me, interfaces and proximity effects are really interesting because they lead to new physics that isn't possible in the individual materials themselves. I didn't really understand your question. I think it was something to do about critical field. Is that the question? Yeah. Yeah, I don't think we can answer that question. We haven't really explored. You're saying is that the critical fields in the triplet case should be distinct from the singlet case. I agree with you. It's not something that we've really explored in this example. Of course, we're only really looking at this field regime where we explore the diode effect. We haven't really explored the critical fields, I have to be honest, because I'm not sure they would be that interesting, but maybe we should.
Okay, another one small issue is that I noticed that the expression of your evidence, like temperature dependence, actually is the same expression like the GL autoparameter. So is that safe to using such methods to confirm the file momentum Cooper pairing? Is that safe? Because this way actually is proposed by first used in your publication. Because you said we observe the diode effect and the delta JC, and it has the temperature dependence.
Yeah.
Is that right?
I think this diode effect is really interesting. It's sort of totally new in the last 2 or 3 years. We have a lot to understand, and in particular, in a way, what's really surprising is that it almost seems to be universal. As soon as you break time reversal symmetry, central symmetry, we've seen it in 4 distinct systems, and there's other work by others on other systems, indium arsenide based systems. So I think it's really a new field, which. Right, as you were asking about this, the G factor seems to be too big. Nevertheless, we think from our experiments we've proven it really is intrinsic. There can be extrinsic origins. So quite a few papers now on just changing, let's say, your Josephson junction, like Jagadish Mudera at MIT is, if you just make one side thicker than the other, then you will automatically get a diode effect, but it's not intrinsic, actually not very interesting. So I think it is a new field, in which, in my mind, the most interesting question really is about how the triplet supercurrent could be passed once created into a magnetic system, and what is the mechanisms by which that could happen, and how can we make it sufficiently transparent at interface? I think this is a very interesting question, so remain to be resolved both experimentally and theoretically.
You mentioned about the interface between the palladium and the YIG is very important to enhance the diode. Yeah. So the palladium is just play as a heavy metal or some brushbar interface.
So that's a very interesting question. This whole question about the interface between platinum and YIG has been extremely controversial for 10 years, with some groups claiming that there is no moment in platinum, and other groups claiming there is a magnetic proximity effect. Well, we're clear in our mind, our experiments show, and I've always believed there is a proximity-induced effect. But as you know, the YIG has a very complicated ferromagnetic structure, and you can imagine there could be structures at the interface where they could cancel one another. So I think this remains a very interesting question.
Professor Parkin, my name is Guodong Li from IOP. Thank you very much for your very interesting talk. I have maybe a general question is, currently the circuit is based on the semiconducting diode. And for the semiconducting diode, if you cool down the temperature to certain temperature, it doesn't work. And your talk is about the Josephson diode, and it mainly based on, if I understand correctly, it's based on superconducting material. So the temperature is also quite low. And if you want to use it, then you need a big cost. But in the temperature range, for example, 100 Kelvin on the liquid nitrogen temperature is quite easy to access. But what's your opinion for this temperature range, based on what kind of circuit can build this kind of a diode?
Well, I think generally speaking that the most interesting logic circuits require diodes. And superconducting logic, there is a field of superconducting logic that operates at ultra low temperatures, but no diode. So with the presence of a diode, you can imagine more efficient logic circuits which use basically smaller form factors. That would be the goal. However, I think your question was more about temperature. And of course, there's no reason why this diode effect, we cannot see it at high, as you mentioned. I think you said liquid nitrogen using cuprate superconductors, it should be possible, for example. Or, of course, as you know, there's a lot of controversy, but there is room temperature superconductivity, at least under super high pressures, at least the work by Michel Eremets at the Max Planck for chemistry in Mainz. So I think it's a rich field. I think superconductivity is a very interesting field, and again, I believe interfaces will be the key. Maybe we could create interfaces that could sustain superconductivity at much higher temperatures, and of course, there's this fantastic work from Professor Schwei's group with the single monolayer of iron selenium on STO, and I think these concepts of interfaces to sustain higher temperature superconductivity is something that I'm very interested in. We're certainly working on. And this concept, I think, of taking two materials, one material to form having the pairing mechanism, and a second material to form the condensate, is a very interesting one, very appealing. And I think this, I mean, on the one hand, superconducting logic is being used for a variety of technologies. With the development of quantum computing, if it develops, and the possibility then of ultra low temperatures being available, at least in the cloud, means that you could really imagine new forms of logic and devices that take advantage of properties of superconductors, diode effects, and dissipationless current flow at, I think, modest temperatures. We've shown these platinum diode effects at 2 degrees Kelvin, and using other superconductors, probably we could see them at much higher temperatures. Certainly not today at room temperature, but maybe in the future. I'm not sure I answered your question, but anyway.
Oh, there's online. We have an online audience, maybe hundreds audience online. So there's a question.
Okay.
So the question is, there are very few works on field-free diode effect, such as Wily polarization-induced time reversal breaking. Yeah. So what else do you expect?
Oh, this is a very interesting question. So this field-free effects are very interesting, and I think there are quite a few materials now that show, which are non-magnetic, that show intrinsic time reversal symmetry breaking for a variety of origins innate to their electronic structure. I think some of these materials will show field-free diode effects. I think I think the phenomenon itself is very interesting, but beyond that, they probably would show these zero field diode effects. I think they should be explored. So I think it's a very interesting. It's a new field in just the last 2 or 3 years. A lot of exciting research directions, including this one, to follow.
Oh, thank you. Do you have more questions? Yeah.
You have showed a view graph which shows the oscillation of this proximity effect as a function of distance, or
maybe that one? No, this oscillates. This one.
No. The theoretical one.
The theoretical one. This one. No, where's it? That one? Oh, wait, there we go. This, that one? No.
No. Not as a function of the separation distance.
Down here? Down this one?
Previous. Further. At the very beginning, I guess.
The very beginning. Okay. Back to the beginning. That's the beginning. This one. This one.
Yeah,
okay.
yeah.
Oh, yeah.
The phase of this wave function.
Yeah.
The right bottom. This is the shape.
Yeah.
So I'm wondering, is there any possibility to use this oscillation to finally prove your results? I mean, to really see the phase change.
Very interesting. So of
this superconducting proximity effect.
Okay. Now this one, what Busten showed was you get S equals 0, 1 triplets generated. So we could not use those to manipulate magnetization. However, as shown here, in this case by Bezier, I don't have his theory, then if you use these non-collinear spin textures, you would also see oscillations. But S equals 1 component of the triplet component of the superconducting order parameter. So just as you said, if you change, let's say we inject in this mechanism, we create from, let's say, an IBM through this non-collinear spin texture, some triplet component, depending upon the distance through this material, we would change it.
Yes. You will change.
Therefore,
you will see the sign change of the superconducting.
Absolutely. So therefore, if we,
I think that will be a definitely the improvement for the superconducting proximity effect.
I think you're totally right. So there's some aspects of the phenomenon that have never really been tested that we could test by building the right structures. Just as you said, maybe lateral geometries in which you would change the spacing, create the triplet supercurrents, then manipulate the magnetic wire, but it has to be low moment. This is what we're doing, and then you should see exactly what you said. I agree. Very interesting.
So I didn't see any more questions. So I have a very naive question. So in order to see this diode effect, you need to fabricate, many different materials layers. So is there possible to realize such kind of effect in a single phase material? So if you have a single phase material that is superconducting and have a magnetic layer that naturally integrates, is it possible?
I think there's a huge opportunity for discovery, and I think so. What I'm showing you this system we built. We built this system where we've connected several different deposition systems: molecular beam epitaxy, oxide chamber, nitride chamber. We built something we call these are the two MB systems you can see now, and then we have a pulse laser deposition. It's connected to an angle resolve photoemission system, and then at the very end it's connected to a glove box. And then it's also connected to a system we built ourselves with up to 44 magnetron, ion beam, and MB sources. We call it Mango. So in this system, we can take a substrate under ultra-high vacuum automatically from one system to another and combine different techniques, exfoliation plus MBE or exfoliation plus PLD or PLD plus sputtering, all these things. So we can create a whole variety of materials. And as I said, interfaces, I think, are the key. The key in all of these experiments. And actually, generically speaking, very interesting because interfaces very difficult to calculate. So today, let's say with Andre Benevig, we've been working with him for a number of years, and he's, let's say, super interested in how many topological materials there are. So what does he do? He takes 500,000 materials from the inorganic database. He's very clever, invents a way so he doesn't need to calculate the whole electronic structure just close to the Fermi energy, and finds out 25% are topological. Totally unexpected. But that's the point. With all these 500,000 materials, you can essentially calculate all their electronic properties. Transport properties, more difficult. Nevertheless, intrinsic properties. However, interfaces, nearly impossible. A, there are infinite number, and B, you don't know how the two materials sit. And it turns out, for example, you grow material B on A, you strain it. However, more interestingly, as we've recently discovered, you can create a strain gradient. The strain gradient breaks the center of symmetry. Time reversal breaks the center of symmetry. And that leads to, for example, vector exchange interactions that won't otherwise exist. So you can take a simple material like cobalt, an alloy, which is cubic, introduced a strain gradient, and now we see skyrmions because we've introduced a vector exchange related to that strain gradient. So strain gradients, very difficult to predict. And it turns out the strain gradient actually has a very interesting dependence on thickness. When it's too thin, you get no strain gradient. Intermediate thickness, you have one. When it's too thick, it's too small. So very interesting in this regard. Interfaces enable you to create entirely new materials, very difficult to predict. So of course, it's very nice to have theoretical predictions, but as an experimentalist, you it's kind of even more exciting when you can use more of your imagination and your innate view of materials. I think that anyway. So interfaces, I think, are the key to the future of nearly all technologies, including this one.
Yeah, interface has many possibilities. Thank you.
Oh, but can I make one final comment? It turns out that I meant to include a slide. The Max Planck Society has a so-called Max Planck Graduate Center. 6 of our institutes in similar fields of research combining together. And that graduate center, I'm one of the directors. Bernhard Keimer is the main director. He's a director in Stuttgart. And we have a program where we encourage PhD students who'd like to come to do a combined master's PhD can apply to this graduate center. So if you know of any fantastic students who'd like to come to Germany to one of these 6 institutes or can work between them, then please let them know. We'd be very encouraging them to come and take advantage of all this amazing infrastructure that we built at my institute and the other Max Planck institutes in related areas. Thank you very much.
Thank you. Yeah, I think we have no more questions, so we'll conclude this lecture. Let's thanks Professor Stuart again.
Thank you.
谢谢大家哈。
这个问